So if our goal is to take the derivative of any kind of function, and you're thinking about what kind of functions do I, the student, know about, you probably start with polynomial functions, but then you'd be like, wait a minute, I know more than that. I know about radical functions and rational functions, and then if you really thought deeply, you might be like, yeah, and also exponential functions and logarithmic functions. Are there any other types of functions that you, the student, have heard of that we haven't talked about already? Well, yes, there are. You probably spent the most recent math class that you ever took studying this exact type of function. Trig functions, things like sine and cosine and tangent, secant and cosecant, etc. That's what we'll talk about in this video. At least some of that stuff. Pictured before you is the graph of y equals sine of x. If we did the argument where we drew a whole bunch of tangent lines and tried to estimate the slopes of those tangent lines, you might start with the tangent line right here at 0. If you had to ballpark the slope of that tangent line, I bet you'd call it 1, or at least some number pretty close to 1. And then as I go to the right here, the tangent lines get less and less and less steep until I get to some point somewhere over in here where the tangent line is horizontal, meaning its slope is 0. What I'm saying is if I was trying to plot the derivative function, I would want the height at 0 for that derivative function to be 1, and I would want the height at this point, whatever that is, of the derivative function to be equal to 0. And I can kind of continue that argument, right? As I go further to the right, the tangent lines becomes negative. How negative? I don't know, more and more negative until I get somewhere in here where it looks like the slope of the tangent line would be -1, give or take. So maybe I throw a point down here at -1. And then I'd continue on my journey of looking for important points that I can plot the slope of the tangent lines to. Over here, it looks like I got a horizontal tangent line again, so that slope is 0. Over here, it looks like the tangent line is pretty damn diagonal. It's not a phrase I planned on saying today. So I guess that slope would be 1, or at least really close to 1. I get all these important points. And then I ask you the question, do you know of any functions that go through all these different points? And if you're thinking in terms of trig functions, maybe you'd be like, yeah, I certainly do. The cosine function goes through all these different points. It might not be as obvious to see the cosine function here because this axis is scaled in terms of units instead of pi's. But if I scale this in terms of pi, here's pi over 2, here's 3 pi over 2, and 2 pi, and all of a sudden maybe it's looking a lot more familiar. Anyways, what I'm saying is that quick analysis seems to imply that the derivative of sine is just cosine. Turns out that it is. I did not prove that to you. I gave you a very weak visual argument to try to convince you of that fact. Could I prove that to you? Well, kind of. I mean, if I were going to prove that to you, I'd probably go back to the definition of the derivative, and I'd try to take the derivative of this function sine of x. I'd say it's the limit as h approaches 0 of the sine of x plus h minus the sine of x divided by h. And then I'd algebraically manipulate the hell out of this thing until I can cancel out this h. Unfortunately, that algebraic manipulation is really complicated. But it turns out that if you do that, you'll end up with the cosine of x as your answer. And you might be like, whoa, how's that work out? What can I do algebraically to change sines into cosine? The trick to it comes from this term right here and the angle addition formula. Do you remember that? Probably not. It's one of those formulas you'd learn in a trig class that says the sine of the sum of two angles like a plus b is the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. When you're trying to simplify this, this is the relationship you use, which changes an expression that only has sines in it to an expression that has sines and cosines. And then you do a whole bunch of algebra and you cancel out some stuff using some properties that we haven't really learned yet. And when all the dust settles, you're left with cosine of x. I know that's kind of unsatisfying for me to just tell you that that works out without giving you a real argument. But we just don't have the algebraic skills necessary to use in conjunction with limits at this point in the class. There's a really cool geometric argument for why the derivative of sine is equal to cosine, and somebody else does it way better than I can. So I'm going to post that video at the end of this section, and maybe you can watch that instead. But the point, what you need to know for our class, think memorization if you want, is just that the derivative of sine of x is cosine of x. That's it. You're like, cool, that's one trig function, but if I remember right, there's like 6 of them, right? Sine, cosine, tangent, secant, cosecant, and cotangent. And that doesn't even get into arcsine and arccosine and all those inverse trig functions. Good news, or maybe it's bad news. We're eventually going to learn the derivative of all that stuff, but a lot of it is way beyond where we are in this class. At this point, all I want you to know is the derivative of sine and the derivative of cosine. The derivative of sine is just equal to cosine. Wouldn't it be cool if the derivative of cosine was just equal to sine? Right? Maybe there needs to be a question mark here. Well, unfortunately, the derivative of cosine is not equal to sine, but it's really close. Look what happens when you take a look at the graph of cosine. What's the slope right here? I assume you mean the slope of the tangent line to this curve right here? Yeah. How steep is the graph right here? Well, the tangent line would be horizontal, and a horizontal line has a slope of 0. Yup. So if I'm plotting the derivative, I should have a height of 0 right here. But then look what happens when I go to the right. The tangent line over here is negative, and it continues to be negative all the way until I get over here past this point where it's also horizontal. What I'm saying is when I plot the graph of the derivative of cosine, it's going to be negative all throughout here. If you plot it really carefully, you'll see something that kind of sort of looks like this. That's too bad. That's not what sine looks like. What sine looks like is more like this. That's terribly drawn, but maybe that gives you the idea. Yeah, it's almost sine. It's just sine reflected over the x-axis. What I'm saying is the derivative of cosine is just equal to negative sine. If you can just remember that the derivative of sine is cosine and the derivative of cosine is negative sine, you know the last two rules that we'll be learning in this ridiculously long section on derivative rules. Instead of just giving you these rules, I should really use these rules in an example problem before I end the video, so I'm going to do that. Can you figure out the derivative of 3 times the sine of x minus 2 times the cosine of x plus pi? This might be a good pause and try it on your own kind of thing. As always, don't forget stuff you've learned in previous sections. What you'd want to do is recognize that this is the derivative of a sum or difference of 3 terms. So we're going to take the derivative of each term individually. This term has a 3 as its coefficient. I can pull those constant multiples out in front and get 3 times the derivative of sine of x minus 2 times the derivative of cosine of x plus the derivative of pi. That's weird. A minute ago, we said the derivative of sine of x is equal to cosine of x. So 3 times the derivative of sine of x would just be 3 times cosine of x. A minute ago, we said the derivative of cosine of x is negative sine of x. So I got negative 2 times negative sine of x. A negative times a negative is a positive. I get plus 2 sine of x. What about the derivative of pi? I know this doesn't look like a constant, but this is just a constant, right? It's 3.141569 something. This is a constant. I don't care what constant it is. The derivative of any constant is just equal to 0. You don't have to write the plus 0. We call this our final answer here. The last of the rules in this section of videos are these 2 trig rules. We don't yet have the ability to take the derivative of any function out there, but we've made a really good dent in that goal. You might not like hearing this, but we've kind of picked the low-hanging fruit. We've taken care of all the easy, in big old air quotes, examples, and going forward, we'll have to consider some more difficult rules. But because they're more difficult, we're going to go through them much more slowly than we did in this section, where the old drinking out of a fire hose analogy feels really apt. You're given a ton of rules. Some of them you may understand, some of them you may just think memorization, but what you'll see is that when you do a bunch of examples of these types of questions on the homework, you end up memorizing these rules without really even trying to. I have a few loose ends to tie up, but I imagine at this point you're so sick of hearing me talk that I need to make these videos really short. So I'm going to end this video here, make one more short one to tie up this section.